Hi everyone! In this video, we're going to be looking at the order of integration for double and triple integrals. So we've done integration before in Calculus 2 and Calculus 1 just a little bit. And then also in a previous resource, I talked about double and triple integrals and how we set up the integration bounds for the domains that we're asked to integrate over. But now we're actually going to learn how do we evaluate those double and triple integrals. And so one thing that we're going to explore is why does order of integration matter and how can we change the order of integration so that it makes some problems more manageable or even actually possible with the order of integration that we have. So one very important thing when evaluating these multiple integrals is that we're working from the inside out. And so what I mean by that is if we had the order of integration dz, dx, dy, well, what comes first is dz. So we're going to integrate with respect to z first, then x comes second, and then lastly, we have y. And so let's look at an example of how we would actually do this integration in that correct order. And so here in our example, we have a triple integral with bounds, and it's being integrated over dz, dy, and dx. So one thing that I want to point out here is we are integrating the function of x. And when we go in order, we're actually going to want to integrate that function x with respect to z because dz comes first. And we're going to use these innermost bounds to do that integration. So I'm actually going to rewrite our integral. Integration is using the same process that we learned in Calc 2. We can use the same rules. The only thing that's changing that we really need to be cognizant of is this order. And so integrating x with respect to z actually is just x times z. And we also can't forget about these bounds. So we're integrating from 3 to 4 minus x squared minus y. And so now we're just going to substitute in these bounds for z because that's what we integrated over. And then subtract the two resulting expressions. So first plugging in 4 minus x squared minus y. And then subtracting x times 3. And so now we're just going to simplify this expression by distributing and then combining any like terms. So here, when we distribute this first x, we get 4x minus x cubed minus xy, and then minus 3x. Combining like terms, the only things that can be combined are this 4x and negative 3x. And when we do, we end up getting negative x cubed minus xy, and then 4x minus 3x is a positive x. So now this is the new function that we're going to be integrating in our next integral that we'll look at. So I'm just going to rewrite our problem that we have left, filling in this new expression for our integral over z. Okay, now next thing to note here is dy is the integration that comes next. So now we're integrating with respect to y, and with our bounds being from 0 to 1 minus x squared. So again, I'm just going to rewrite this so we only focus on this integral. In practice, as you get more and more comfortable working with integration across multiple integrals, you can do this all in one step if you want to. But I choose to just separate it so that we can focus on it. All right, so integrating with respect to y, we are going to get a negative x cubed y minus xy squared over 2. And here we're just using power when we're evaluating this integral from 0 to 1 minus x squared. So again, plugging in these bounds for y, since that's what we just integrated with respect to, and then subtracting the resulting expressions. So here we get negative x cubed times 1 minus x squared minus x times 1 minus x squared squared over 2 plus x times 1 minus x squared. Now I could write this out, but to save a little time, I just want you to point out that if I were to plug in a 0, or when I do plug in a 0 for my y, each of these terms becomes 0, and so therefore we just end up subtracting a term of 0. And then we are going to do a lot of distribution here, and then simplify by combining like terms. So first thing I want to do is let's do this 1 minus x squared all squared off to the side here. So remember when we do that, it means we're multiplying that expression by itself 2 times. So we get 1 minus x squared minus an x squared plus an x to the 4th power. Don't forget your power rules. When we multiply x to a power, we end up adding the powers. And so then simplifying this, we get 1 minus 2x squared plus x to the 4th. So we'll end up plugging that in for here in just a second. So distributing this negative x cubed, we get negative x cubed plus x to the 5th power minus x times this expression we found over here, 1 minus 2x squared plus x to the 4th all over 2. Plus distributing this x, we get x minus x cubed. Still have a little bit more distribution to do because we still have this x times this set of parentheses. So we end up having negative x cubed plus x to the 5th power. And then distributing this negative x, we get a negative x over 2, because again, don't forget this divided by 2 here, plus 2x cubed over 2. And then minus x to the 5th over 2 plus x minus x cubed. So combining like terms, we have a positive x to the 5th power and a negative x to the 5th power over 2. And so 1 minus 1/2, we get a positive 1/2 x to the 5th power. And then we also have a negative x cubed, a positive 2x cubed over 2, which 2 over 2 just becomes 1. And then we have this negative x cubed here. And so combining all those, a negative x cubed plus x cubed, that just becomes 0. And then we still have a minus x cubed. And then lastly, we have a negative x over 2 term and a positive x term. And so here, adding the coefficients, we get 1 minus 1/2 is a positive x over 2. All right, so now we're going to go ahead and we're not done yet. We're going to replace our integral with respect to y with this new expression and copy what we had left. So our bounds we still have are 0 to 1. And then our expression is 1/2 x to the 5th power minus x cubed plus x over 2 with respect to x. So evaluating this, we get 1/2 x to the 6th divided by 6. And then we have minus x to the 4th power divided by 4 plus x squared over that 2 that we still had, but then now using that power rule of integration times the 2 of our new power. And then we're evaluating this from 0 to 1. First, I'm going to do a little simplification though. So 2 times 6, multiplying our denominators here, we end up getting 12. And then 2 times 2 here, we end up getting 4. And so evaluating this from 1 to 0, just like we've done in all the other times. So substituting 1, we get 1 to the 6th power over 12 minus 1 to the 4th power over 4 plus 1 squared over 4. And then minus, so if we plug in 0 for our x, all these terms, because they'll have a numerator of 0, become 0. So we end up subtracting 0. Remember, 1 to the 6th power, 1 to any power is going to get us 1. And so we end up having 1/12 minus 1/4 plus 1/4. Well, a negative 1/4 and a positive 1/4, those become 0. And then all we're left with is 1/12. So that is the value of the integral over the bounds of integration we were given. All right, so now that we know how to evaluate and obey the order of integration that we're given, we need to think about how can we change the order of integration. So why would we need to? Well, if we looked at this example that we have here, we have the integral from 0 to 1 over dx, and then integral from x to 1 over dy of this function e to the y squared. So according to order of integration, we would integrate with respect to y first. But look at how complicated this integral would be because we have y raised to a power, all this in the power of e. And so there is actually no elementary antiderivative for the integrand e to the y squared. We would actually need some sort of technology to help us even accomplish this. So in that case, how could we even possibly evaluate this integral? Well, in order to do so, it would actually be a lot simpler if we could integrate with respect to x first and then take care of the integration with respect to y. So this is one example of why we would actually need to change the order of integration. And so let's actually go ahead and change the order. So first thing is, many of you might think, okay, well, if we're changing the order, shouldn't we just change dx and dy so that dx comes first? And then since we changed these, we'll just change the bounds. See, but if we did this, we would then have in our final answer an x. And that is not going to help us actually find a value of anything. That's just going to have us have an expression with x in it. And so in order to get rid of that and make this so that it is possible, we need to actually reevaluate the bounds. So yes, we can change this order, but we have to actually do a little work to see what our new bounds are. So this we cannot do. So in order to change the bounds, I'm actually going to draw a picture of what these bounds are telling us here. And so I'm going to draw a little graph. So right now, since the bounds for y integration is from x to 1, that tells me that my y is varying from the value of x to the value of 1. So on the y-axis, y equals 1 is about here. So I'm just going to draw a line there. It's not a great line, but so this is when y equals 1. And then, like I said, it's also could have be as low as the value of y equals x. So here's y equals x. Now, the bounds for x, it can vary from 0 to 1. So the y-axis is when x equals 0. And then right here is where x equals 1. So right now, this is the area that we're integrating over. So if I want to change my order to be dx dy for this function e to the y squared, well, our first integration bounds are going to be for x. And so we want to fix x between something that is a constant or a function with respect to y, since that's what we would be integrating over next. So I can actually vary x from 0 to, instead of x equals 1, actually this line y equals x. So 0 to y equals x. And this is how we're going to vary x. Now, the thing is that, yes, this may be a very simple function here, but it's not always going to be in all of your problems. So when I rewrite this y equals x, I want to put it in terms of y. That way we can actually have it so that, oh yeah, I finished x, so now all of my x variables are gone after evaluating with these bounds, and now I'm only dealing with y's. And so we're going to say this is from 0 to y. And then if that's the case, we're now looking at, okay, what y's where we have no x's in our bounds could describe this area of integration. And so that is when y varies from 0, so the x-axis, all the way to 1. And so here we change that. And this is our new integration problem, which is way more manageable for us to evaluate. So just one thing, so I showed you an example to change the order of integration for a double integral. Triple integrals are going to actually be very similar, but in that case, instead of just considering the bounds of x and the bounds of y, we need to also consider the bounds of z. So instead of just dealing with the xy plane, we're actually looking at the xy plane, the yz plane, and the xz plane to find those bounds of integration. I hope you find this video helpful, and I wish you luck as you evaluate your double and triple integrals.